So chapter 9 is another one of these chapters that there's not a whole lot of new information that's presented. It's kind of a review or kind of an expansion of a lot of earlier information. So again, this first section here I kind of has as one of the 5 main skills is kind of making sure we understand and review concepts from earlier chapters, like thinking about 3 modes of bonding, whether it's ionic, covalent, or metallic. And we kind of relate that to concepts we learned in our last chapter. So we learn about relating ionization energy and electron affinity to the formation of bonds between elements. And then also kind of thinking about energetics of processes. The idea that if we want to have a favorable energetic process, that means we're going to be going downhill in energy. And then we kind of start building in some information that's going to take us through the last 2 chapters of our course here, which is thinking about how to draw structures of molecules. So we start very simply, as we're talking about atoms here, drawing what we call Lewis dot structures. So representing the electrons in atoms as dots that surround the chemical symbol. And so we'll build on that in chapters 10 and 11 as we finish out the course here. So some key things that are kind of new to this chapter but kind of bringing in some earlier information is thinking about ionic bonding and importantly what we call lattice energy. And so lattice energy is the attractive force, and it seems a little bit weird to think about, but it's the attractive force between gaseous ions. So a gaseous cation and a gaseous anion, huge attractive force that hold those species together and what creates in reality that ionic bond that holds those species together. So we'll go through what equates to essentially a Hess's law type problem to add up all the costs and benefits for making an ion when we think about formation of an ionic bonding compound. Then we move on to covalent bonding, and again thinking of sharing in electrons, and think about some properties that deal with covalent bonds. And again, this is going to be material that we build on as we think about structures of covalent compounds in chapters 10 and 11. But we'll think about things like bond order, which has to do with whether it's single, double, or triple, and then bond length and bond strength. So again, bond length we're going to rationalize by thinking about bond order and so forth. So we'll have a lot of examples that we'll do with that. But truthfully, there's only 4 sample problems that we'll work through in this chapter. Another kind of Hess's law type problem that we'll think about is dealing about bond energy and chemical change. So up to this point, this is going to comprise the 3rd way now that we can think about the delta H for a reaction, for an unknown reaction. We've learned in other chapters that we can do Hess's law. If we're given a laundry list of equations, we can manipulate those equations to get an overall enthalpy for a reaction from the sum of those equations. So that again was Hess's law. Another way that we learned about was using Appendix B and the delta H of formation values. We basically can imagine taking all of our reactant species and breaking them apart to their resultant elemental species, and the same thing with our products. And we take products minus reactants and we can think about it in that way. So this is kind of similar to that, but rather than imagining the delta H of formation or the formation of our reactant and product species from their elemental kind of starting points, we're actually going to imagine breaking every single bond in our reactant species and forming every single bond in our product species. And what we're going to consider is the fact that breaking bonds in our reactant species is going to be a cost, and then forming bonds in our product is going to be a gain. And so it's going to be a cost-benefit analysis to determine whether the enthalpy for the reaction is exothermic or endothermic. So we'll have a sample problem that we'll work through with that. The last section here kind of gets us set up very nicely to think about kind of polar molecules in chapter 10. So we'll think about polar bonds, and that all has to do with electronegativity. So when we're having elements that bond together covalently and are sharing electrons, if those electrons aren't shared equally, then we have what's called a polar bond. So we'll go through the rules to kind of think about whether or not a bond is polar in just a few minutes here when we go through some sample problems. But that's basically the 5 main skills for chapter 9. Again, an important table that we'll utilize is table 9.2, which basically shows all kinds of different covalent bonds and their worth, their value in terms of kilojoules per mole. Okay, so we are going to begin this, this chapter by looking at a sample problem that depicts ion formation. So this first problem from chapter 9 asks us to use partial orbital diagrams and then also Lewis symbols. So we'll kind of treat these as two separate problems, but we'll depict the formation of sodium cations and oxide anions from their atoms, and then think about what this means to create the ionic compound that's going to be made. So again, let's start by using the partial orbital diagrams. We'll do that first. So if we show sodium, sodium really just exists with a single 3s electron. And again, if we look at the periodic table here, right, here's sodium. So sodium as neon as its kind of previous noble gas. So we've got essentially a 3s 1 electron. So looking at this in terms of a partial orbital diagram, not an electron configuration, an orbital diagram, we can depict it like this. And we know that we're going to have two of these, because if we look at what oxygen looks like, so we're going to have oxygen. Oxygen, again, being in row 2 of the periodic table, is going to have a 2s orbital that's filled over here, and then the 2p orbitals are going to have 4 electrons in them. But again, if we draw that properly, here is the 2s orbital being filled, and then if we look at the 2p orbital, again we're going to have 4 electrons, but we have to follow Hund's rule, which tells us they're going to fill like this. Okay, so now we're going to have, and we're going to show this, anytime we draw arrows, we always like to show the movement of electrons. So the movement of electrons shows that sodium is giving up an electron, and one of those electrons is going to go and sit in this p orbital, and the other electron is going to go sit in that p orbital. So again, if we have these two reactants coming together, the product that we would form is we're going to form 2 sodium cations, and basically this is isoelectronic with neon. So really not an orbital diagram to show. It would have this empty 3s orbital, and then the underlying 2s and 2p orbitals would be filled. And then we're going to have oxide, so O2 minus, again just drawing what we already knew what was happening from up above, is this 2p orbital is now going to become filled as it gains those 2 electrons from sodium. And again, now we also have something that's isoelectronic with neon. Both of them have noble gas configurations, and everybody's happy. Formula of the compound, again, is going to be Na2O, and we would call that sodium oxide. Don't ever forget that chapter 2 was a really important chapter to think about bonding and then nomenclature of these bonded compounds. All right, so last part here is to use Lewis symbols for this. So again, just another way to depict the movement of electrons. We're going to have 2 sodium cations, and then our oxygen anion is going to have 6 electrons that we're going to display around its atomic symbol. Each sodium is going to give 1 electron to, again, this open p orbital in oxygen. And I should have mentioned, when we're drawing this Lewis dot structure for oxygen here, it's filled such that it looks very much like the orbital diagram that we have here. We don't draw it like this. We don't draw it with 6 electrons like this. That's incorrect, because that would imply that there's a p orbital that has nothing in it, and that's not the case. We can see that from here. So again, a good way to think about kind of drawing these is if you draw your oxygen atom, start by going 1, 2, 3, 4, 5, 6. And then I'll make sure that you have the correct number of electrons that are unpaired. So again, each of these sodiums transfers its electron to the oxygen, and we're left with 2 sodium cations that for all intents and purposes do not have any valence electrons that we're going to depict. And now oxygen, having 2 extra electrons, is going to have a -2 charge. Again, an attractive force that exists between these ions is going to have them form the ionic salt, sodium oxide.